All right, hey guys. In this video, we are going to take a look at Chapter 2, Section 3. We're going to talk about the derivative function. And the first thing we're going to do is we're going to look at a certain function, and then we're going to graph its derivative based on how the function looks. And then we're going to go backwards. We're going to look at the graph of the derivative of a function and then sketch a possible function. In the next video, we're going to look at section 2.4 and talk about interpretations of the derivative. So let's get going. All right, so last time we talked about a derivative being a function, and we can graph functions. We can graph lines, parabolas, cubic functions, quartic functions, etc., etc. So as I mentioned, the first thing we're going to do is we're going to start sketching derivatives just based on what a function looks like, and then we're going to take the sketch of the derivative and try to graph a possible function for it. So just a recap of what we looked at last time, we have this definition of a derivative. And so the definition of a derivative tells us that the derivative is the same thing as the limit as h goes to 0 of f of x plus h minus f of x all over h. And remember, we found derivatives this way in the previous video. And so, for example, if we were given a function f of x equals x squared, we use this definition right here to get the derivative by plugging in x squared in for f of x and plugging in x plus h in for x squared. So this is just kind of a recap of what we did last time. F prime of x is going to be equal to 2x. And so, you know, both of these are functions that we can graph. The actual graph is going to look something like this, x squared. And then 2x is going to look something like this, okay? So here we have a function and its derivative. So the first example we're going to do is pretty classic. We want to sketch the derivative of the function, and this function happens to be a line. So remember that the slope of a line is constant, right? It's always, no matter what 2 points you pick on a line, the slope between the 2 points are going to be the same, right? And that's what we're looking at when we graph derivatives. So for example, here maybe this is the point -3 right here. And so what we want to know for the graph of our derivative is what is the slope of the tangent line to this point? Well, we know what the slope of this line is, right? Rise over run. And so it looks like we're rising -2, running 1. And so we know that the slope of this line is -2. And so the slope of this tangent line is also going to be -2. Right? And actually, any point on this line is going to have, you know, the tangent line to it, which is actually equal to that line. And the point is that the slope is always going to be at -2, no matter which x value we pick. The slope is always going to be -2. So when we graph this, when we graph the derivative function, I can look at a bunch of x values, let's say -3, -1, 0, and 1, and my y values are all going to be the same. My f prime of x is just the slope of the tangent line at each of these x values, and that slope is always going to be -2. So if I was to graph this derivative function, maybe I'll do it in green. So if I were to graph this, it would just look like this. So f of x is my blue function, and f prime of x is just this horizontal line at -2. Okay, what if we had something like this? So we have a parabola looking thing, and we want to sketch the derivative. Well, again, we're looking at the slope of the line's tangent to each of the x values. So, for example, this could be x is equal to, I don't know, maybe -1/2. X equals -1/2. There's my slope. It's a positive slope, fairly steep, and then it starts to flatten out as we get higher and higher x values up until the point x equals 1. The slope's going to be 0 because of that flatness on top of the curve. Okay, so positive, positive, positive. At x equals 1, the slope's 0. And then we start getting more negative, 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 right? And so we can sort of estimate what's going on. And again, this is just going to be a super rough sketch. And so at -1, I know that the slope is going to be positive, and it's fairly steep, so I'm going to put 2 positives there to represent a steeper slope. At 0, it's still positive, but it's kind of flattening out a little bit. So I'll just put 1 positive there. At x equals 1, it's flat, so that's going to be 0, right? The slope of that tangent line is 0. And when we hit, maybe I should put some intermediate values here. If we do 1.5, the slope is negative. And then it starts getting more and more negative as the x values increase. So at x equals 2, it's going to be even more negative. And again, this is just going to be a super rough sketch. So let's go ahead and graph our derivative. Let's do it in green. When x is equal to -1, we have a pretty positive number. So I don't know, right here, this is a positive y value. When x is equal to 0, we have another positive y value, but it's not quite as positive as the last one. So maybe like right here, maybe. When x is equal to 1, that slope is 0, and so it's going to go through this x-axis right here. When x equals 1.5, we have a negative slope. When x is equal to 2, we even have a smaller number than that. And so we're getting what's kind of looking like a line here. So this guy is f prime of x, my derivative. And again, f of x is just this parabola. Okay, so select the correct graph. Well, actually, let's just say sketch the graph. So we're going to sketch the graph of the derivative of this function. So, all right, let's get some key points here. So we are going, if we draw our little tangent lines, we have a negative slope, negative slope, negative slope up until we get to this point. We have 0 slope. And then we start going upward, up, up. And then we have 0 slope again, and then we start sloping downwards again. Okay. So this is how my derivative is behaving. And so let's just kind of make a little rough t-chart of x and f prime of x. So it looks like when x is equal to -4, if we just look all the way to the left, we have, a fairly negative sloping tangent line. And then as we get closer and closer to -2, it starts to sort of drop off, right? So maybe at -3, it's still negative, but maybe not as negative because the tangent line's flattening out to 0. And then at -2, it appears to be 0, that slope. And then it starts increasing. So at -1, we have a positive slope. And then it starts to kind of flatten out again at that hump, which is right here. So that hump, it looks like it's like at, I don't know, 2 or 2.25, something like that. So let's see. So that's going to be 0, and then it starts going downwards again, and it seems to be rapidly decreasing. So just go negative, negative. All right. Okay, cool. So now that we have this stuff, we can go ahead and graph the derivative in the same plane as the function. So at x equals negative 4, f prime of x should be negative y value, right? And so, I don't know. And again, guys, we're just sketching this. It doesn't have to be, super accurate. We just want a good picture, but again, it doesn't have to be super accurate. When x is equal to negative 3, it's still going to be negative, but not quite as negative. Maybe like that. Maybe. Negative 2, it's going to go to 0, or y value 0. At negative 1, it's going to be slightly positive, maybe like that. And at 1, it's going to be still positive, but it's going to dip down a little bit. 2.25, it's going to be 0. And at 4, it's going to be negative again. So maybe something like this. And again, it's not a great, beautiful work of art, but it'll do for our purposes. We're just kind of estimating in this lesson. Okay, sketch a graph that could represent the slope at every point of the function below. So again, if we're talking about the slope of the function, we're talking about its derivative. It's just a fancy way of saying find the derivative. Okay, so let's go ahead and do this. So we're given the function, we're trying to find the derivative, and so we can talk about tangent lines. So here we're sloping up. It looks like about here it's 0, and we start sloping down again until about here, where it's 0, sloping up. At that hump, it's 0, sloping down. This hump, 0, and then we start sloping up again. Okay, so we kind of have a rough idea of what our derivative function should look like. X, f prime of x. Okay, so let's look at x equals negative 3 first. We're sloping upwards, and so this is going to be positive. And it starts to flatten out at, looks like it's flattening out at about negative 1.75. We have a slope of 0, this horizontal line right here. And then it starts sloping down. So we have a negative. And I'm comparing these two negative slopes. It looks like this one is a little bit steeper than this one, so I'll put 2 negatives here. Okay. And then from 1 to 3, it seems to be sloping upwards. And it's a little bit flatter than this one, so I'll just put 1 positive sign there to indicate that. And let's see, where is this slope 0? Looks like about 3.5. X is 3.5. That's going to be 0. And then we start sloping downwards from 4. And that looks a little less negative than the first 2 negatives we put. Okay, so let's see what else we got. Right, okay, and so then it looks like about 7.5. This thing is 0 again, and then it starts sloping up. Okay, so let's go ahead and just kind of sketch this out. All right, so -3, we have positive number right here. -1.75, we have 0. It's going to cross the x-axis right there. -1, it's going to be fairly negative right here. At 1, it's going to be positive, but not quite as positive as the as this guy right here. Okay, so we did this, and at 1, we're going to be, I don't know, right here maybe. 3.5, we have 0. 4, it's going to be negative. 7.5, it's going to be 0. And 8 is going to be positive. All right, so then we just connect our dots, make a smooth-ish kind of curve. And there we have it, a rough sketch of our derivative. Okay guys, I am going to go ahead and stop the video here. I'll see you guys in the next part. Thanks for watching. Hey guys, in the last video we practiced graphing derivatives from functions, and in this video what I want to do next is do some examples where we're going the other way. So we're given a graph of a function's derivative and we're trying to find a possible function that could match it. And so we saw in the previous video that when the derivative f prime of x is positive, the slope of the tangent line to the function f of x is positive. And if f prime of x is negative, the slope of the tangent line to f of x is negative. So if we have this curve down here, let's say that this is our function f of x, this curve. And remember that we have this guy right here is going to be have a negative derivative because the tangent line is sloping downward at every point on that interval. And so here f prime of x is negative. And also right here, oops, let's try this again. And also right here, f prime of x is going to be negative. So right here, again, at every point on the curve, if we draw lines tangent to those points from, it looks like the interval -2 to x equals 1, every point is going to have a tangent line that has a positive slope. And so in this case, f prime of x is going to be greater than 0. Okay, so let's talk about going the other way. All right, so if we have the graph of a derivative, so if we have f prime of x and it's positive on an interval, meaning it's above the x-axis, then our original function f is increasing over that interval, okay? If the derivative is less than 0 over an interval, then f is decreasing over that interval, okay? So it says based on the graph of f prime of x, where is f of x increasing and decreasing? So we have this example right here. This is our derivative graphed. And when our derivative lies above the x-axis when it's positive, we know that f is increasing. So I can already see that since it's above the x-axis here, it's going to be increasing right here. And it's also going to be increasing here. Oh wait, not there. It's going to be increasing like that. And then when f prime of x lies below the x-axis, in other words, f prime of x is negative, then the function's going to be decreasing there. So it's going to be decreasing right here, right? Because this whole portion lies below the x-axis, and so does this portion right here. Now, when the derivative is 0, we know what that means, right? We have two situations. We either have, kind of a flattened curve like this, where we have a minimum, or we have something like this, where we have a maximum. So this happens when the derivative is 0. Right? Because remember that if the derivative is 0, then that means that the slope of the line tangent is going to be horizontal. Or it's going to be 0 rather. The line's going to be horizontal. Okay, so those tangent lines are going to look something like that. All right, and so we have a couple of places where our derivative function crosses the x-axis. That's where we're going to have those flattened areas on our original function. Right here, and right here. And so one thing to note is this fact that if we're going from increasing to decreasing, we're going to have sort of this upside down parabola looking thing here. So a relative maximum, if you will. If we're going from decreasing to increasing, we have this guy, relative minimum, if you will. And so again, we're just doing a really rough sketch, and there's some different possibilities of what f of x could look like. So this is just, the one that I'm about to draw is just one possibility. Doesn't mean that yours is incorrect, but this is just one possibility. So the first thing I'm going to do is I'm going to draw my little orange flat parts where the derivative is 0. Okay, so I'm going to draw my original function in the same plane as the derivative function. So I notice that at this point right here, I'm going from increasing to decreasing, okay? And so based on this, if I'm going from increasing to decreasing, I have kind of a flat shape right there at this x value, okay? So let me go ahead and do that. So I have a little flat section, maybe it looks like that, where the peak is going to line up with this x value there. All right, so I'm going from increasing to decreasing there. Now, right here, I'm going from decreasing to increasing. Okay, so I'm going to have this little guy right here. All right. And then finally, right here, I'm going from increasing to decreasing again. So I have this guy. And then I can just kind of connect the dots and sort of follow the rules, right? So it tells me that when x is equal to 0, all the way up to x equals 0.5, this thing better be increasing. It better be climbing up. So what that means is that my regular function is going to be climbing up, 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 up. Maybe it looks like this, and then it's going to flatten out right there. And then my function starts decreasing, all right? So it starts decreasing at x equals 0.5, and it's going to get smaller and smaller and smaller up until x equals 2. Okay, so this thing's going to, maybe it'll, oops. Shoot, why did it do that? Okay, so maybe it'll look like this, maybe. Oh, let's see. Maybe I'll do that a little bit. Okay, so it's decreasing, decreasing, decreasing. Again, this isn't going to be a beautiful picture, but I think you get the point. Now, it's supposed to connect up with this little parabola here at x equals 2, and so I'm going to kind of just shift it downwards a little bit so it connects up. Maybe like this. Oops. Maybe like this. All right. Okay, and then at x equals 2, it starts increasing again until x equals 3. So up, 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 up until x equals 3. And then we can see the parabola sort of flattens out, so I'm going to move that orange guy again so that it meets up. And maybe it looks like that. And then it starts to decrease again after x equals 3, so maybe it looks like this. Okay, so yeah, so let's, I'm going to actually trace this in purple just so we can, no I'm not, I'm going to trace it in, let's do another color. How about yellow? I'm going to trace my function in yellow right here. Okay, so this is a possible function. Okay, and this yellow is going to be f of x, whereas the one with the bunch of colors that we were given was the derivative. Okay, so we use the derivative we use the derivative to find a possible f of x. All right, let's do this one. The slope of a certain function at every point is graphed below. Sketch a possible function. So when we say the slope at every point, that's a key phrase meaning derivative. All right, so we're given a derivative function, and we want to sketch a possible function that maps to that. So the first thing I notice is that this derivative is 0 right here, so I know that's going to be kind of flat right there. And the derivative is negative all the way from x equals -4, it looks like, until x equals 0. And then the derivative is going to be positive all the way here, okay? So that's what my derivative function looks like. And now I'm going to go ahead and sketch my regular function. So this thing is going to be flat, and we're going from decreasing to increasing, so it's going to kind of look like this, right? Okay, so it's decreasing, right, from x equals -4 all the way onwards to the left up until x equals 0. So maybe it looks something like this. And then it's going to meet up with our little parabola. And then it starts increasing from x equals 0 onward. Okay, so it kind of looks like a little parabola here. So I'll go ahead and trace this in yellow. So this is my regular function, f of x. And I got that by looking at the derivative function and seeing where it was positive and negative. Okay, let's do this example. Okay, sketch a possible function whose derivative is graphed below. So again, I only see one spot where this thing is 0, the derivative is 0. And it looks like the derivative is always going to be positive because it's always above the x-axis, which means that our original function is constantly increasing. Okay, and so our original function, maybe we could have something like this. It's increasing, 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 getting flatter and flatter. It's pretty flat right there, but then it just keeps increasing, increasing, increasing. So it could look something like that. So again, the yellow is my regular function, the green is my derivative. Okay. The next section that we're going to talk about is how to interpret the derivative. And the first thing I'm going to do is introduce a new notation. So the first thing we looked at was this limit definition of a derivative. So that's one way to denote a derivative, the slope of the tangent line to a point on a curve. We can also have y prime if the function in question is y. And we can also have f prime of x, which is the one you'll see probably the most. But we have this new notation right here, dy dx. This is called Leibniz notation. So Leibniz was a co-inventor of calculus along with Isaac Newton. And this notation is named after him because he created it. So let's talk about what this means. Okay, so here it is, dy dx. And so basically what dy dx is just the derivative. It's all this means is the derivative. Okay? And what it means is, you know, without introducing limits, we're assuming that dy is sort of like the change in y, and dx is like the change in x. And Another way you can think about the D is D for delta, delta meaning change. So yeah, when delta x is very, very small, then dy dx is going to represent the slope of the tangent line, okay? So, for example, like if we have this curve right here and we have a point, x comma y, and then, we add on a very small value of x, which is dx, we can talk about the limiting process this way. So, when dx approaches 0, this thing should approach the derivative, right? The slope of this line right here. Okay, so this is going to be dy dx. And the way that we say this in practice, okay, dy dx means the derivative of y with respect to x. And all that means is that y is our dependent variable and x is our independent variable. So y depends on x. That's what the respect means, okay? Hey guys, in this video I want to do some examples where we're interpreting the derivative by using Leibniz notation. So the cost C in dollars to produce G gallons of a chemical can be expressed as C equals F of G. Using units, explain the meaning of the following statements in terms of the chemical. So the first one is F of 200 equals 1300, and the second one, we're talking about derivatives, F prime of 200 equals 6. So the first thing we need to do is figure out what is the independent and the dependent variable, or what is going to act like our x and our y here, right? Because in Leibniz notation, we have dy over dx, and so we need to figure out what's acting like our y and what's acting like our x in this problem. Well, they tell us what's acting like our x, that's the input here. And so this guy has to be our output. And so C is going to depend on G here. And so instead of dy dx, we're going to have dc dg. And what are the units for this? Well, C is in dollars, okay, so it's going to be dollars per gallon. So these are the units. All right, so, okay, going back to part A. So this is pretty standard function notation. We have an input, we have an output. And so this is telling us that when we produce 200 gallons, it's going to cost $1,300. Okay, so that's what part A is telling us. Now let's go ahead and look at part B. So part B, since we're dealing with derivatives, we're dealing with rates. And so this is saying the derivative when, x or g equals 200, the derivative is going to be 6. And derivatives are rates, right? And so 6 what? Okay, so it's going to be $6 per gallon, right? This is our dc dg, okay? So what is this telling us? Well, it's telling us at 200 gallons, the instantaneous, right, derivative, instantaneous rate is $6 per 1 gallon. And so if we produce one more gallon, so like 201 gallons, for example, if we produce one more gallon, then the cost should increase by $6 approximately. So that's what this is telling us here. Let's do another example. If Q equals F of P gives the number of pounds of sugar produced by a manufacturer when the price per pound is P cents, what are the units and the meaning of F prime of 30 equals 50? I encourage you to pause the video and see if you can do this and see if our answers match up at the end. Okay, so again, we want to figure out what is our independent and dependent variable. Well, since P is our input, that's going to be our independent, acting like our X, and Q is going to be acting like our Y. And so remember, we have dy dx. Well, in our case, it's going to be dq dp. And what are the units? Well, Q, what's Q? So Q is the number of pounds, all right? So this is going to be in pounds per, and P is going to be in cents. So pounds per cent, that's our units here. So F prime of 30 equals 50. What is this telling us? Well, remember, this is defining the derivative at P equals 30 to be 50. And remember, our derivative is a rate, right? So it's going to be 50 pounds per cent. So this is telling us what is the meaning? Well, at 30 cents, the instantaneous, the derivative, the instantaneous rate, I think I spelled that wrong. The instantaneous rate of production, perhaps, is 50 pounds per 1 cent. And so we should expect that, at 31 cents, our production is going to go up by 50 pounds. Let F of T be the depth in centimeters of water in a tank at time T in minutes. What does the sign of F prime of T tell us? Well, F prime of T, again, we're talking about derivatives, and so Leibniz notation is a good way to think about the units, the ratio. And so what is our independent variable? That's T, right, because that's our input. So T is acting like our X. And that's in minutes. And then F of T, our dependent variable, is going to be in centimeters, right? And so we have that Y is F of T. Okay, and so dy dx, remember, in this case, it's going to be df, or df of t if you like that, over dt, change in time. And so what are the units? Well, they tell us that the units of f of t is in centimeters and the units of t is in minutes. So this is going to be centimeters per minute. That is going to be my rate here, okay? So this is my derivative, dy dt, f prime of t, same thing. And so what happens if it's negative? What is it telling us? Negative centimeters per minute. Well, it's telling us whether the depth is increasing or decreasing, right? If it's negative, it's going to be decreasing. If it's positive, it's going to be increasing. All right, so that's what the sign tells us. Now let's interpret this. F prime of 27 equals 18. What in the world does that mean? Well, again, this is our input, so this is our t, right? And so they're telling us that at 27 minutes, the rate at which the depth is changing is going to be 18 centimeters per minute. Okay, so that's what that's telling us. Let's see, I think we have 2 more examples. Okay, so the temperature H in degrees Celsius of a hot cup of coffee placed on the counter is given by H equals F of T, where T is the time measured in minutes since the coffee was put on the counter. So the question is F prime of T positive or negative? Is the derivative positive or negative? Well, let's think about this. So first of all, let's put this derivative business in Leibniz notation to better understand the units. So in this case, our dependent variable is H, which is in degrees Celsius. So we have dH, right, our dependent, over dt, okay? And the units of H is Celsius, right, degrees Celsius. Maybe I shouldn't put equals. Maybe I'll just put an arrow. Celsius. Oh, gosh, I can't spell either. I hope that's spelled right. If not, it's okay. And T is going to be in minutes per minute. And so the question is this positive or negative? The question is, when we put a cup of coffee on the counter, how is the temperature changing? Well, the temperature is obviously going to be going down because it's cooling. I mean, unless you put it back in the microwave or something, but it's going to be consistently cooling, and so it's losing degrees for every minute, right? Okay, and so that is going to tell us that this thing is negative. Why? The coffee is cooling, and it's losing degrees per minute, okay? What are the units of F prime of 24? Well, we just kind of answered that in part A. The units is degrees Celsius per minute. So those are the units. What is the practical meaning of F prime of 24 in terms of the temperature of the coffee? Well, that, again, when we think about prime, that's the same thing as derivative. We want to think about rates of change, right? Instantaneous rates of change. And so that's telling us that, since this is our T, this is telling us at 24 minutes, the rate at which the beverage, the coffee, is cooling well, we don't know. It's going to be some negative degree per minute. Some negative degree per minute. Okay. Let's do one more. A tank is being drained of water. The function V gives the volume of liquid in the tank in liters after t minutes. And we want to interpret the statement. The slope of the line tangent to the graph of V at t equals 7 is equal to -3. So let's parse this piece by piece. Now, when we talk about slopes of lines tangent, we're always thinking derivatives. Derivatives, rates of change, slopes of tangent lines. These are the three things that are all the same. So they say the slope of the line tangent is -3, so that's our rate, okay? Now, what is our independent and dependent variable? Well, v, so t is unless stated otherwise, t is always going to be our independent variable. The volume depends on the time that passes, right? And so what we have here is we have dv over dt, and this is going to be in liters, they tell us, per minute. So this is the rate at which the tank is draining, liters per minute. And so they tell us the rate. They tell us that it's -3, and so that means that that the tank is being drained at -3 liters per minute. And it makes sense that it's negative, right? Because it's draining. And this happens, they tell us when this happens, when this rate, when this instantaneous rate occurs. This happens at t equals 7. And so this instantaneous rate occurs at t equals 7. Okay. And remember, the whole point of calculus is to study functions that don't change at a constant rate. In algebra, we looked at functions, in Algebra 1, Algebra 2, we looked at functions like this, where the rate of change was constant, right? Like, if we were talking about a linear function where something's draining, I don't know if such a thing exists, but if, let's say that there was, and it's draining at -3 liters per minute, well, at every time it's going to be draining at the same rate. However, that's not usually the case. Usually we have a function that looks something like this, and so what we're finding here is, say that this is 7 minutes right here on our independent axis. Let's see, this is t equals 7 minutes. So this is telling us that this instantaneous rate, this slope of the tangent line right here, is going to be -3 liters per minute. And okay, guys, well, that is the end of this video. I'll see you guys in the next lecture. Thank you for watching. Appreciate it, and see you next time. Thanks.